The missing component in our cosmological model is dark energy. Evidence for dark energy was found in 1998 in observations that showed that the universe was accelerating. This is the observation. What you're seeing here is the distance modulus against redshift for a number of type 1a supernovae. What this is showing is that these type 1a supernovae are dimmer than you would expect in a matter-dominated universe. Let's understand what it means and how it leads to the concept of dark energy. So the first thing is that type 1a supernovae, they are a binary with a white dwarf and a normal star. As we already studied, white dwarfs have a mass limit because of their equation of state. As you accrete mass onto a white dwarf, eventually you achieve the mass limit, the ultra-relativistic limit, the Chandrasekhar limit, where the electrons will be moving at the speed of light and they start implodes. The implosion leads to a supernova. So this happens in a binary system because the white dwarf is slowly accreting matter from a normal star and inching towards the Chandrasekhar limit. Now, because all the explosions happen at the Chandrasekhar limit at the same mass, they are very good standard candles, meaning that they all would have the same absolute magnitude. If you measure several type 1a supernovae over different distances in the universe, you would be able to do a magnitude distance relationship. This is what is done here on this plot. Every point here is a supernova. I mean, the different points are different surveys, but they all agree on these lines. What you're seeing here in the lines are three different cosmological models, and here is the residual. The long dashed line is a universe of only matter. And as you see, it fails to reproduce the observation, meaning that the supernovae are dimmer than what you would be expecting from a universe that is closed and only of matter. Omega is equal to 1. Now, what does this represent? That if the supernovae are dimmer than a universe of only matter means that they're further from us than is predicted by this universe, means that the universe has expanded more than what this model allows for. If we go back to the models where we calculated the evolution of the scale factor, a model of omega matter equal to 1 is this here, the black line. If they're further out, means that the universe has expanded more. The scale factor is bigger compared to a scale factor in the past than what you would predict, meaning that you would favor a model with less matter, opposing the expansion, and therefore expand it further out. But as you see, even that model with the present amount of matter that is observed, about 0.3, is not really the best model either to explain the observations. As you see, there are more points at the dimmer side than you would expect. So that implies that there must be something else, either making the supernova dimmer or having made the universe expand even more than you would expect with the matter that is present now. In fact, even a model with zero matter does not match the observations. So these are different cosmological models. Omega m here is the amount of matter. Omega lambda, which is also present in the other model, is the amount of dark energy. We're going to get to that soon. But what you're seeing here are different models with different amounts of matter. What you see here is this line, the purple line, which is a universe of zero matter and also zero dark energy. You see the residual is a bit too low. The supernova would be a bit dimmer, and that doesn't account for any matter whatsoever. If you want to add matter to the universe at the present proportion, about 0.3, you need to add something that makes the universe expand. As you see here, these supernovae are at about redshift 1, which is half of the age of the universe, about 7 billion years. So from 7 billion years up to now, something else has been making the universe expand faster than what you would be expecting. And in fact, faster than what you would have if the universe had no matter whatsoever. So the only way to reconcile that is something that is accelerating the expansion of the universe. Now, this is a very disturbing conclusion. We have been considering that the Friedman equation has only two components. One is the kinetic energy of the expansion of the universe, And second is the gravitational attraction of the matter that is inside the universe. Now, matter is gravitating, so it is only decelerating the expansion. That's what one would be expecting. You would have the kinetic energy of the expansion, and then the counteracting the expansion, the gravity of the matter that is pulling in it. You would be expecting, therefore, that even though the universe is expanding, this expansion will be decelerating. To find out that the universe is actually accelerating is akin to throwing a pen upwards and find out that it is not decelerating, stop, and falling, but actually moving upwards and upwards with ever growing speed. This discovery was so fantastic that it led to the Nobel Prize in Physics in 2011. The discovery was in 98, that's this article. It is the most cited article in all of astronomy with more than 12,000 citations and counting. Now let's see the interpretation of this acceleration in terms of this mysterious dark energy that is pushing the acceleration of the universe.